Okay, today we're going to start off our discussion with spontaneous reactions. So, just a little bit of a review. We started out with entropy, which was the disorder. Then we went to enthalpy, which was the heat of the reaction. Now you're going to see we're going to combine the enthalpy with the entropy and temperature to get a new equation that is dealing with free energy. But the first thing we're going to talk about here is a spontaneous reaction, which is a chemical reaction that is known to produce the written products. As opposed to a non-spontaneous reaction, which does not give the products under the specified conditions. Remember, certain things require certain situations. For instance, I always go back to the magnesium ribbon that we put into the crucible. If we do not heat that crucible, will that magnesium ever react? No, it will not. So, if I would have the equation magnesium plus oxygen yields magnesium oxide, if I did not include that heat, that reaction wouldn't proceed. So, it has to be under given conditions. So what a non-spontaneous reaction is that it will not yield those products under the conditions that are given right there. A spontaneous reaction will yield the products with the specified conditions. Now, these do not refer to the rate at which the reactions proceed. All it refers to is whether they will proceed or not. So it says nothing about the rate. If it is spontaneous or non-spontaneous, it just depends on whether it will happen at those specified conditions or not. We have two factors that determine whether a reaction is spontaneous or not. The entropy, which was the S, and the heat that was released or absorbed by the reaction, which is the enthalpy. So two factors will influence whether a reaction is spontaneous or not. Okay, free energy is the potential energy contained in a reaction system. The energy that is available to do work. We have two different types that relate to whether it's a spontaneous or a non-spontaneous reaction. The first type is an exergonic reaction. Once again, you see that EX and you think what? Outside, leaving, exiting. Exergonic is a spontaneous reaction that releases free energy. Ender, once again, you see the endo, you're thinking inside. An endergonic reaction is a non-spontaneous chemical reaction that will absorb free energy, which means that we must do some work in order for that reaction to proceed. So, exergonic releases free energy, endergonic absorbs free energy. Which leads us to Gibbs free energy, which is delta G. The numerical value of delta G is negative in a spontaneous process because free energy is lost by the system. The numerical value of delta G is positive in a non-spontaneous process because free energy is absorbed by the system. So one thing you might want to add on to these things, okay? If delta G is negative, it says it's a spontaneous reaction. But is it exergonic or endergonic? Exergonic. So you might want to put that in parentheses, that if delta G is negative, it's spontaneous, but it's also exergonic. If delta G is positive, it is non-spontaneous, but it is also endergonic. And down there in the bottom in red, put an asterisk by that, circle it, do whatever you have to do, but you need to make a mental note, because on your data tables, entropy values are given in joules per mole, not kilojoules. So look at your data table right now. Look at your data table right now. Look at the value for delta H and delta G. What are those labels? Kilojoules per mole. Look at the value for delta S, or just the S. Those values are what? Joules. Can you subtract the kilojoule from a joule? It's not going to work. So we're going to have to convert. And what we need to do is we're going to convert the joules to kilojoules. You're going to see here. All right? So make sure, biggest problem that we have with this is people not converting the S or the entropy values. When that does not happen, we've got problems. Okay? So make sure if you're using the Gibbs-Helmholtz equation that you convert those values. Now, I told you that there were two different ways to calculate these equations. We're going to use example 1, graphite here. Actually, we're going to use graphite plus oxygen yielding carbon dioxide for both of the examples that we're going to work today. But for the first one here, it says determine whether the following reaction is a spontaneous reaction by using delta G sub F for the reactants and the products. So, I'm going to give you a second here to copy this down. I'm going to pause it here. Now, doesn't this reaction right here look very similar to what we have been doing? So what do you think the difference will be? Huh? Yeah, it'll be a different column on your table. So I want you to look at that middle column, the delta G column, because that is the one that we'll be using for this. So what I'm going to do is I'm going to find my delta G values, and I'm just going to write them right above these over here. So I find carbon dioxide is negative 394.4. My graphite and oxygen both have delta G numbers of 0. So go ahead and find graphite. It's on the front page of your new chart. Go ahead and find oxygen. Both of those values are 0. So when I take my products, I'm going to get this equal to negative 394.4 minus 0 plus 0. So using this particular equation, I'm going to have a value of negative 394.4, my label, kilojoule per mole. So if I were to ask you, is this a spontaneous reaction or not? What would you tell me? Why would you tell me yes, Ethan? Because it's a negative value. If I were to ask you, is this endergonic or exergonic, you would tell me exergonic. Why is it exergonic? Because it's a negative value. So this is nothing new than just using the same old products minus reactants, but it's a different value on your data table. Now, the thing that's a little bit different, folks, is the second way in which we calculate this. And right here, I said delta G is negative, so the reaction is spontaneous. We just discussed that. Now here is the second way to calculate this. So I'm going to give you a second to copy down this slide, and then we're going to roll with it. Okay, the example states that using the Gibbs-Helmholtz equation, determine whether the following reaction is spontaneous at room temperature, which is 25 degrees Celsius. They give me the same equation that I've just been using. Carbon is solid graphite plus oxygen gas yields carbon dioxide gas. Now, the thing about this is the question specifies that I need to use the Gibbs-Helmholtz equation, which is this equation right here. Okay? This equation right here. So what I am going to do is I am going to calculate each one of those separately. So I'm going to calculate the enthalpy, I'm going to calculate the temperature, and I'm going to calculate the entropy. So how I do it is I just separate them into each individual one. So if I have this, if I have the enthalpy, I know that it's products minus reactants. So I'm going to go through and look at my enthalpies. I'm going to write them up here, my values to start with. So carbon dioxide is a gas. Enthalpy is negative 393.5. Carbon as graphite is 0. Oxygen gas is 0. So when I come down here, I'm going to have negative 393.5 minus 0 plus 0. So my enthalpy is going to be negative 393.5 kilojoules per mole. I'm just going to write those over here because I do not want to have to go back on the slide. 393.5 kilojoule per mole. So that is my enthalpy, delta H. What's my T going to be? My T is nice and easy because I take the 25 degrees Celsius and I add to it 273.15 to convert it to Kelvin. So I have 298.15 Kelvin. My third and final calculation is the entropy. So I'm going to go through and I'm going to get entropy values for carbon dioxide as a gas, for graphite, and for oxygen. Well, now I have actual values, so I'm going to have to do the math. So I'm going to take 213.7, and from that I'm going to subtract Now remember that I don't have any coefficients in front. So I do not have to multiply those values by anything. But if I would have coefficients, I would have to multiply them through, like we did before for entropy. So when I do my calculations, okay, I get a value of 210.686. So I'm going to take 213.7 and I'm going to subtract 210.868 and I'm going to get a value of 3.014, but my label is in joules. Okay? My label is in joules, mole, Kelvin. So how am I going to convert that into kilojoules? How do I convert that into kilojoules? I move the decimal to the left 3 spots. 1, 2, 3. So it's going to be 0.003 3014 kilojoules mole Kelvin. I don't know why I have an S there. Now, I'm not done yet. I'm not done yet because I've got all the values I need now. I've just got to bring them back into my Gibbs-Helmholtz equation. So, delta H was negative 393.5 kilojoules per mole minus my T, 298.15 Kelvin times 0.00314 kilojoule mole Kelvin. Be a little tough, but I'm going to close my bracket right there. What are we talking? Oh, yeah. I'm missing a 0 in there, aren't I? Right here? Yes, I would agree. My bad. 0.003014. So that value is going to give me a 0.8986. And if I cancel my labels, it's going to give me kilojoules per mole. I have this value, negative 393.5 kilojoules per mole. So when I subtract that value, I get negative 394.40 kilojoules per mole. So were my values the same either way I did it? Look back to example 1. That was the same value, right? It's just two different ways to get at the same value. Obviously, the first example is easier than the second, but you need to know how to do both of them because you will be asked to do both of them. Now, tomorrow we will be working some more examples of these. Okay? So tomorrow we'll be working some more examples of these.